Okay, 3, 2 was addition of whole numbers. 3, 3 is going to be subtraction of whole numbers. There's going to be some interplay between the sections, obviously, but there's going to be some new information as well that's related specifically to subtraction that didn't happen with addition. So the first thing we'd like to do is to define what we mean by subtraction. So for any whole numbers a and b, where a is bigger than b, a minus b is the unique whole number c, such that a plus c is equal, I'm sorry, I read that wrong. B plus c is equal to a. And just a real quick example to write it down. This kind of looks like our definition when we did less than, actually. It's very similar. If I have 1 is less than 4, right? What this is saying is that I'm able to subtract 4 minus 1. I'm able to do that. And that answer, whatever it is, let me just put question mark for the moment. I know we know what it is, but just put question mark for the moment, is going to work because there is a 1 plus that question mark, which will equal 4. There's a number we can fill it in with. And of course, the question mark is 3, right? So 4 minus 1 is equal to 3. It's another whole number, and the reason it works is because 1 plus 3 is equal to 4. Almost identical to our definition of less than in the last section. Okay, there are 3 models for subtraction. Are you ready? Okay. Model number 1 is the takeaway model, and this is the one that people generally gravitate towards. In fact, if you asked my children before we started realizing that they kept saying this, to do a subtraction problem, they would have called it a takeaway problem. That's what they would have called it. And I'm like, no, it's subtraction. And no, it's not minuses either. It's subtraction. It's called subtraction. We're going to use the right word. And so apparently along the way, I'm sure they've had math teachers who've used that phraseology, and that's why they're doing it. This is the takeaway model. So Abby had 24 rocks. Eli sneaked into her room and took 5 of her rocks. How many rocks does Abby have now? Okay, you had something and now it's not there. That's the idea of the takeaway model. So we're going to draw an image for this. And our image is going to be rocks. And so here are my rocks. Maybe if I can make them thick, I can actually make them filled in. There's a rock. That's a pretty good rock, right? I need how many of them? 24 of them. There's 6. 12. 18. Uh-oh. Last one, 24. Okay, there's her 24 rocks in her room. Hers would have been colorful rocks. There was a time when my daughter liked to go and get those colored rocks at like the zoo. You know, I'm talking about the really pretty ones. Everywhere we go, she collected rocks. It was really funny. All right, so we've got 24 rocks. Eli sneaks in the room. He takes away 5. So we remove 5 of them from our collection of 24 rocks. And we could literally count the number that are left if we needed to, and we would end up with 21. 21, was that right? I wrote that wrong. 19, sorry. For some reason I was thinking you had 26 to start with. 19 rocks. Oh my goodness. It's going to be one of those days. Okay, so this is a concrete picture for this, but the idea in the word problem part of it is always that I have something and I'm removing something from what I have. That's the idea for a takeaway model. We all good? Model number 2. Missing add-ins. Lisa needs to collect 10 leaves for a school project. She and Temeskin go out and find 8 leaves. How many more leaves does Lisa have? This question should feel different than the last question. I don't have something and I'm taking something away. I need something that I don't have all of it yet. I'm missing something. So this is a missing add-ins perspective. And so with this one, what I'm going to do is I'm going to draw what I have, which is my 8 leaves. Great leaves. And I'm missing some, right? I need some more. And how many more I need will actually end up making the total 10. So these are the ones that I'm going to add in that I need to still go find. And the answer is these ones that are in sort of this dotted look at the end. So I need 2 more leaves. Okay, are we good? Model number 3 is a measurement model. Akeem drives 15 miles to the mall, and as he's on his way home, his mom calls and asks him where he is. He states that he's coming home, and he's driven 8 miles so far. How far is Akeem from home? Okay, so we don't have something to take away. We don't need something and find it, although sometimes those things present themselves within this problem too. What's happening in this model is that we're actually measuring something, we're not counting something, right? The first one we were counting rocks, and in the second one we were counting the leaves. Now we're not counting leaves, we're measuring, in this case it's a distance. So it wouldn't have to be distances, but you see distances used a lot with measurement models. It could be measuring cups of flour, right? Or something like that too. And so it doesn't have to be lengths in this way, but it's some kind of a quantity that we're measuring, not counting. So as we're taking a look at this one, we know that he is 15 miles to the mall. Or I should say the mall is 15 miles to his house, right? So this whole thing is 15. And it says that he is 8 miles back towards home. Make it look a little bit more realistic. He's gone this way and there's 8 left here. And the question is, how much further does he need to go? Let's try to make that dotted. Let's make it a little bit better. Can you see that that's dotted? That looks good. Okay, so how much further would I need to go to get all the way up to 15? So in some sense, this is like a measurement model. I didn't say that right. Like a missing add-ins model is what I meant to say. I'm missing the piece that adds up to 15. But because it has this sort of distance feel to it, we treat it a little bit differently. And the answer here would be what? 7. He needs to go 7 miles further. Okay, so here's what I want you to do. I need you to move. All right, so is everybody's partner here today? Who's Mackenzie's partner? Okay, so Lily joined with a different group. So everybody find your partner. Go ahead and move. And when you move, we're not going to move back because it just doesn't need to move. You don't have to move at all, do you? Okay, so move to where your partner is. What you're going to do is you're going to create a word example, right? Word problem for each of our 3 models for subtraction. Okay? There's 3 models. There's takeaway, missing add-ins, and measurement. And you're going to create an example. You don't have to solve it. I just want you to write a word problem that would use that model. Does everybody understand what you're doing? Okay? Be prepared to speak at least one of your word problems out loud. Okay? So, be appropriate and those kinds of things. Just saying. You're going to say something out loud. Don't be shy. Okay? So feel free to write those in, and we'll pause for a moment while you do that. Okay. I need a volunteer to tell me, what did you create for your takeaway model? I'm going to volunteer somebody if you don't volunteer for me. Ethan.
Chesney had 1 coconut. Dr. Bello ambushed her and stole her coconut. How many coconuts does Chesney have?
Excellent. It's not true. It didn't happen? Okay. All right, so we had objects, this time a coconut, and then they were taken away. Good. All right, somebody else for that one. A takeaway. Okay, go ahead, Riley.
Maddie has had 12 goldfish in a tank. Robert adopted 7 of Maddie's goldfish. How many goldfish does Maddie have?
I'm glad that he adopted them. They didn't just die off. Yeah. That was very forward thinking that the goldfish were adopted. Thank you for that. Yes. Okay, good deal. Excellent. Goldfish, and then some of them were adopted away. All right. All right, what's next? Let's do the second one. Missing add-ins. Somebody who hasn't given an example. Abby.
Dr. Hans has 14 tests to grade. She has completed 8 of them. How many does she have left?
Excellent. Dr. Haynes has some tests and they're getting done. That's wonderful news. All right, somebody else who has B, missing add-ins. I've only got 2 groups left. Who's talking?
Jack needs to read 10 books. So far he has read 6 books. How many more books does he need to read?
Excellent. Books to read, and we haven't read them all, so then we're going to read the rest of our books. Okay. That means you guys are left to do my measurement model. Go ahead, Jocelyn.
I'm very proud of this one.
Excellent.
So from OBU, it is 1,258.9 miles away from Disney World. Jocelyn stops for gas in Baton Rouge, Louisiana, which is 580.9 miles away from OBU. How much further does she have to go?
Excellent. Okay, so one thing to keep in mind, just for an FYI, you guys may have been doing it on your last one too, I was trying to hear but I couldn't tell for sure, is that we're still going to use whole numbers. So just take off your 0.9 and we're good to go. Yeah, that's fun. I like that. All right, somebody else tell me your measurement model. Does anybody else have one you'd like to share? One more. Be bold. All right.
Dr.
Man, we're still all about the coconuts and Dr. Bellows. Is that the name we're saying? Dr. Bellows?
Yeah.
My goodness. No, we have not. He's very excited about his coconut, huh? Wow. Okay. Oh my goodness. Okay. All right, let's gather back together. Okay, let's take a look then at properties. Excuse me. We're going to look at the 4 properties that we had for addition and decide which of these properties hold for subtraction as well. The first one is the closure property. So remember, closure meant for addition that if I took 2 whole numbers and I added them together, I was guaranteed to get another whole number. Does that work with subtraction? Katie says no. Why not? Can you give me an example?
8 minus 6.
Try again.
Oh, 6 minus 8, sorry.
There we go. That'll work. 6 minus 8. So 6 minus 8 is not an element of the whole numbers, right? I get a negative. I don't get a whole number. So closure with subtraction with whole numbers doesn't work. Now, if we had integers, it would, right? If we had the positives and the negatives, this would be closed. It would be fine, but it doesn't work with whole numbers. So what we're creating, by the way, are called counter examples. Do you remember hearing about that? We did that back in chapter 2, I believe. Counter examples. All right, how about a commutative property? Does the commutative property hold?
No.
No. Rayleigh, can you give me an example?
I'm trying to think of 3 minus 1
Okay.
and 1 minus 3.
3 minus 1 does not equal 1 minus 3. I mean, all it takes for it to prove, like, this isn't proving by example, we're disproving. Disproving something takes one example. So that's why I'm giving you one example. If one example fails, it fails to have that property, okay? So yeah, there's no commutative property. How about the associative property? The answer is no. Do you want to try and create one for me, Abby?
Okay. In parentheses, 7 minus 5 minus 1 does not equal 7 parentheses 5 minus 1.
Okay, so, and you chose good numbers. The order you chose them in is really nice because it's all still whole numbers. So that was very forward thinking on that. If I do 7 minus 5, I get 2. 2 minus 1 on the left-hand side would be 1. But on the right-hand side, I'd start with 5 minus 1, and 5 minus 1 is 4, and then 7 minus 4 would be 3. Yeah, associative property doesn't hold. How about the identity property? Do you remember what the identity property was? It had the number 0. 0 was our identity element for addition. And it said that if I took that number 0 and I added it to A, either 0 plus A or A plus 0, that I would still get back A.
Yes.
Okay, so give me an example of what you think for, I know this isn't a proof, but give me an example of why you're thinking that it works. Okay, 2 minus 0 does in fact equal 2, right? There's a problem though. 0 minus 2 doesn't. So an identity property has to work in either order. So because this is failing to be commutative, the identity property is also going to fail to hold. So this is another no. So all of our properties failed. There are no properties for subtraction with whole numbers. Okay, these properties, some of them do hold for integers, but they don't hold for whole numbers. Okay, so just like with addition, what we're going to do next is we're going to look at some algorithms. Remember, algorithm just means a way of doing something. So we're going to take a look at some subtraction algorithms. Some of them have the same name as the other ones we saw in the addition section, and they're going to work the same way if they have the same name. So like this one is a concrete model. Concrete model is the idea of actually having those base 10 blocks out and actually using them, right? That's what the base 10 or what the concrete model is. So if I've got 34, I'm going to represent that as longs and units. And if I had a 3-digit number, I'd use flats and such too, okay? So this is 34. So this is 1, 2, 3 longs, and then we've got 4 units. Okay, pretty good so far. And we're going to think of it much like we do a takeaway. We're going to remove something from this. In particular, we're going to remove 18. 18 is 1 long and 8 units. Now I can remove one long from this, no problem, right? But I don't actually have 8 units visible right now to do that. What would I have to do to be able to remove 8 units? I need to break apart one of my longs. Okay, so what I'm going to do is I'm going to sort of remove one of these long pieces, and I'm going to change it into 10 individual units. They should all be the same size. They're not going to be. So this is my broken apart long over here. And once I've represented my picture of 34 in this way, now I can actually remove 18. So I'm going to take away, excuse me, one long and 8 units. That leaves me with one long and 6 units left. Okay, so even though we are obviously not wanting our kids to use concrete model forever, it's a really good intro, and it's a really good thing for them to be able to see and to work with, because even as they're moving forward and they're doing other algorithms later, they have this visual imagery that they can fall back on and understand why it is that they're doing what they're doing, especially when it comes to sort of longer subtraction problems and so forth that are in their future. So, okay, any questions on the concrete model? Okay, model number 2, standard algorithm. This is the one you know. So 34 minus 18. Okay, so with this model, we start on the right-hand side and we go to the left, right? That right to left thing's a little bit awkward, but it's what we do. And we say, okie dokie, I'm going to try to do 4 minus 8, and we're going to say we don't have enough to do that. And so we regroup, or the phrase you might have remembered using is borrow. We take the 3 and we call it a 2. And we regroup. Sometimes people write it like this, like the 1 like beside the 4. I'm going to actually write out what we have. We actually have 14. And the reason we have 14 is because when we borrowed the 1 from the 3, we actually changed a 30, right, like our 3 longs, into 2 longs, or the number 20. That's what's happening to that value. It didn't actually change the value. It changed the way it looks. And then I'm able to do the subtraction. So I've got 14 minus 8 is 6, and then 2 minus 1 is 1. So I have 16. That's the standard algorithm. We've seen that one now for both addition and subtraction. The expanded algorithm is kind of a merging of the concrete model with the standard algorithm so that you can see part of it sort of drawn out a little bit better, but it doesn't actually involve the image of the longs and the units. So what we do, if you'll remember, is that we write 30 as 30, I'll write it this way, 30 plus 4. And we write 18 as 10 and 8. And I put subtraction because I want to make sure both the 10 and the 8, which comprise to make 18, both get subtracted. And when we do this, we say, okay, again, I can't do 4 minus 8, just like I couldn't in the others, right? I have to regroup. And so you can actually see what happens to the 30. The 30 becomes a 20, and those 10 actually shift over and join the 4 to be the 14. So you can see the 10 move a little bit more directly in this algorithm. And we can subtract. So I have a 6, of course. I have a 10 here, of course. And I end up with 16. So it's kind of a blending of the last 2 models together. Okay, there's one more. The last one is going to feel a little bit like it mimics opposite change, which is a model we had in addition. It's a different model, but it's feeling like that. This is called equal additions. So what equal additions does, just like the opposite change with addition did, is that you're going to write it in a sort of a vertical format like this. And your goal is to get zeros, but you specifically want to get zeros on the bottom, okay? So we do not want, okay, well, I should actually say what the goal is. The goal is to not borrow. That's the real goal. The goal is I don't want to borrow. But the way that we're going to not borrow is by getting zeros to show up in these placeholders on the bottom. Okay, as many zeros as we need to do the subtraction easily. Okay, does everybody make sense of that? So the 8 needs to become a 0, and you can do that by adding 2. Okay, now with opposite change, we added 2 and we subtracted 2, right? But with equal additions, we equally add them, okay? So we add 2 to both. So imagine what that's actually doing. So if one of you were to come up here and stand next to me, you're either going to be taller or shorter than me, right? Whatever we are. But if we both then step on a step stool that's the same height, 3 inches taller, our height difference is still the same. That's what's happening. We've equally added something to it, but it's going to make numbers that are easier to work with. So we have 836 and we have 160. I can't stop here though. Why?
We still have to borrow.
I would still have to borrow. There's a 3 in the tens column and a 6, right? So I don't want to stop here. Now I've got to deal with the 6. What do I have to do to the 6 to make it become a 0? Add 40, right? So I'm going to add 40, again, top and bottom. So this becomes 876 and 200. And at this point, I can subtract. Why? I don't have to borrow. 676. Does that make sense? Equal additions. Okay, so we're going to test ourselves on these different bases on these different algorithms by looking at them in different bases. We did that in addition to, didn't we? Okay, so we kind of think we maybe understand it kind of in base 10, so we're going to delve a little bit to what it looks like in base 8 and base 3. Yeah, base 8 and base 3. So we have 3, 4 base 8 minus 1, 7 base 8. And I will walk you through kind of some different ways to think about this, kind of like what we did when we were doing it in addition. So we'll do the standard algorithm first. That's the one that is sort of our go-to naturally. I can't do 4 minus 7, right? So I'm going to regroup. But when I regroup and I take away 1 from here, I don't borrow 10. How many do I borrow? I borrow 8. Okay, in base 10 we borrow 10, in base 8 we're going to borrow 8. So I'm going to borrow 8. Can you picture that with your concrete model? You're taking a long, and the long has 8 in it, and you're breaking it into 8 individual units now. So you had 7, you had 4. You have 4, and you're combining that with an additional 8. How many do you actually have? 12, right? There's a 12. 12 individual unit objects. 12 minus 7 would be 5, and then 2 minus 1 would be 1. And this is base 8. So this is 1, 5, base 8. I want to show you what it looks like with equal additions next, okay? Equal additions, 3, 4 minus 1, 7. Remember, the goal is no borrowing. So I would have to borrow, as evidenced by the one I just did, right? And I don't want to borrow, so I want this 7 down here to become a 0. How many do I have to combine with the 1, 7 for the 7 to become a 0? 1. Right? It's like you have a long and you have 7 individual units, add 1 more unit to it, it's going to make it a long. So this number becomes 2, 0 or 2 longs at the bottom, on the bottom number. What about 3, 4? It's 3, 5. And then in the subtraction is really easy, isn't it? I actually think equal additions is more intuitive on this one than the standard algorithm is. It's very quick. Now, that partly is happening just because of the numbers that are being used here, right? Like, we get that. Not everything's as easy in one direction as it is in another direction for different values and so forth. All right, you want to look at another one? Okay. So we're going to do base 3. And we're going to do standard algorithm first. 1, 0, 0, 2. Minus 1, 1, 0.
So when we're writing it like in an equation like that, we don't need to put that 3 under it.
In the setup for the solving, you don't, but your answer needs to include it. Yeah, did I include that in my answer over here? I didn't in my last one. I did it on the first piece and then I forgot. Yeah, it would be in the answer only. All right. So in the ones column, it's perfectly fine. I can subtract 2 minus 0, no problem, right? So we're good there. We just bring it down. But in the threes column, that's my next column over, I cannot do that. And if I move over to the 3 squareds column, there's nothing there either. So I have to keep moving until I find something, and that's in the 3 cubes column. So I'm going to take this 1, and I'm going to borrow from it, so it'll make it a 0. How many do I borrow when I borrow in base 3? 3. I borrow 3. So this becomes a 3. But I need to borrow from that too to move back over to the original column that I was working with. So this 3 will become a 2, and the 0 will become a 3. All right? Okie dokie. And then we're able to subtract. So in the 3's column, remember I'm calling it the 3's column because we're working in base 3, so its powers of 3. I have 3 minus 1, which is 2. And then I have 2 minus 1, which is 1. And this is in base 3. So 1, 2, 2, base 3. Okay. Let's see. What method do I want to do? I wrote equal addition down, but I just did that one. How about let's do the expanded algorithm? That'll work. So with the expanded algorithm, we'll do this our last example, last piece of an example. We're going to write this out in expanded form. So this is in the 3's column. This is 3 cubed is where I had it. This is 1 3 cubed, 0 3 squareds. Another 0. Yeah, 0 3's and 2 1's. And then underneath it, I'm subtracting 1 3 squared, or subtracting 1 3 and 0 1's. 0 1's or 1 1? What's the number there? 0 1's. So in moving things over, again, I can take 2 units or 2 1's and take away 0 1's and still end up with 2 1's. So this is 2 1's at the end. But I can't do that until I get over to the far column again. So I'm going to remove one of these 3's, and I do that and I change it to an additional 3 here. It looks a lot the same as the other one. And then I have to keep going one step further, remove one of these, and make it an additional 3 here. So when I'm subtracting, I have 3 minus 1 is 2 3's, and I have 2 3's, and then 1 3. Did I mess something up before? What did I do? 1 2 2. No, it's the same thing. Sorry. No, I'm good.
Squared on the 3 at the bottom.
I am missing that. You're right. That's probably why I was looking at it funny. Okay, so I end up with 1 2 2 base 3.